We've selected 3 case studies that we feel adequately demonstrate how Optimus can be used with your mathematical simulation software and how Optimus can enable you to get much more out of those tools that you are already using. So the first case study is going to be Optimus being integrated with MATLAB. We'll demonstrate how you can increase the use of the tools that you already have, that you can spend much more time running MATLAB and getting more results out of MATLAB. The second case study that we'll talk about is using a tool called MapleSim, and we'll show you how you can very easily parameterize a very complex simulation model. And then finally, we will display or demonstrate how Optimus, the functionality within Optimus, can easily be distributed to tools such as Microsoft Excel that you and that many of your engineers that you work with are extremely familiar with already. So the first case study that we have here is a beam. It's an FEA simulation that's conducted inside of MATLAB. For this particular application, we're looking to change or to optimize the mass of this beam given a few parameters. One of the parameters, of course, is the height of the beam. And then we also want to find and to spend a little bit of time looking at the position of these notches. And as you can see, we have actually 4 discrete positions and 3 discrete lengths that this knot, or heights, that this notch can be. We do want to minimize the mass that this beam has while maintaining a particular stress value or staying under a particular stress value. The program has been created inside of MATLAB with a number of design variables, including the load, the anchor location, and things like that. But for this optimization, we only want to vary those 3 inputs that I previously mentioned. The variables that MATLAB will output, there are a couple of different variables. Some are simply scalars, other are actual matrices. And the 3 that we'll be looking at are mass, the displacement, the magnitude of displacement, and then the maximum stress. So in setting up this process, the first thing that we need to do is actually sketch out the workflow that we're planning to use or that we're planning to implement. So as we've mentioned, we first want to identify the inputs that we're going to be changing. And so here you can see we've sketched out the inputs. Then we need to identify the M files that we're going to be using and include any libraries that those M files need to execute. And finally, we need to determine what's going to happen with the scalars and the matrices that are exported or that come out of MATLAB. In order to make this a very streamlined and a very easy process for the users, Optimus has created, or we've developed, a node that allows the user to simply identify the M file that they're going to be working with, and then Optimus automatically finds the inputs that are available inside of that file and also the outputs that are available inside of that file. In addition, it automatically detects whether the output is a matrix or a scalar or an array. This is done with, as you'll see in a moment, with just a few very simple clicks. Now let's begin talking a little bit more about exploring the design space and the optimization itself. We do have a few constraints on our design space. We've already stated that we want to minimize the mass, but we need to maintain a height of the beam between 0.08 and 0.12. The notch position as I previously mentioned, is one of 4 discrete locations, and the length or the depth of that notch is one of 3 discrete points. We do have a constraint being placed on our maximum stress, and using this design space and knowing with the understanding that we have a number of discrete inputs, we've selected or we've determined to go with an adjustable full factorial design of experiments. This is a unique feature inside of Optimus that allows you to actually set the number of levels which you want to run on your factorial experiment. And then the optimization method is another unique method inside of Optimus. It's referred to as a self-adaptive evolutionary algorithm. It works extremely well with discrete optimization problems. And so now we'll jump over and we'll actually do a live demo. All right, so this is, for some of you, this may be the first opportunity that you have to actually see the user interface of Optimus. It's designed to be very user-friendly, very streamlined, and allow you to get your work done as quickly as possible. You'll notice the workflow looks very similar to how it did when we sketched out the workflow. We have our inputs on the left side where we've identified the type of input, the discrete integer input, varying between 1 and 4 for the notch position. We have our call to MATLAB, including the library files for MATLAB. And then we have our outputs. The purple triangles are matrix outputs that we refer to inside of Optimus as vectors. And then the red shape is the actual output, so a single value output. So let's take a look at that node that integrates with MATLAB. So I'll double click on the node, and you may notice at the bottom of my screen that MATLAB has actually been launched. And we very quickly see the input files that are associated with this fembeam.m file. I can select the inputs that I'm interested in and add those to my workflow. And on the output side, we specify the M file that we're going to be using, and Optimus actually runs MATLAB, so we actually run the M file, and we get the outputs that are exposed during that run. And you'll see the matrix and the scalar values. So after we've created our workflow, we're ready to begin with a design of experiments. And as Mike mentioned, this is a very powerful way to explore your design space and to see exactly, to get a much better understanding of what's happening in your design. We would select an adjustable full factorial and then specify the levels that we'd like to see with each input variable. So since we have 4 levels for the position, 3 levels for the depth, and the height is a continuous value. So I'll just select 5 there. And we're immediately told that there's going to be 60 experiments run as part of our design of experiments. So we'll hit apply, and this will actually launch and begin running the design of experiments. And while that's running, we'll go back over and talk a little bit about what information we're going to get from this design of experiments. Mike previously showed the correlation chart. The correlation chart tells us the influence that the inputs have on the outputs. We notice that the changes in the notch position and the notch depth have very little influence on the overall mass, but they do have a significant influence on the maximum stress that's seen. So this is some information about the design which we didn't previously have. In addition, we will be able to create a response surface, a mathematical approximation on the model. Now the DOE is completed, and I've actually previously created a response surface on that design of experiments that you can see being shown here. And then I'm ready to run an optimization on that response surface. So we can select the response surface, and you see just with a few number of clicks, we select that we want to minimize the mass, and we select our self-adaptive evolution. Select apply, and very quickly, perhaps even before most of you can see, the optimization has run 345 experiments on that response surface. We can evaluate the optimum design, and we see that we were able to reduce the mass by about 10%. So overall, we want to take a look at how Optimus helped with this particular simulation. Now we know from simply by looking at the amount of time that it took to run all of these simulations that we would have saved about 75 minutes. In addition to that, in the last 5 minutes that we've been talking about it, I was able to run over 300 calls to MATLAB. This is something that would have been extremely time-consuming otherwise. So we find that we're able to get more intelligence, more information about the design, and that we're also able to reduce the amount of time that it takes to run an optimization, in this case by more than half. Now I'd just briefly or quickly like to discuss Optimus being used with MapleSim. MapleSim is a physical modeling tool. It's an extremely advanced simulation tool that can integrate many different types of physics simulations. This is the interface for MapleSim. For this example, we're doing a hybrid electric vehicle optimization, and you can see all of the different parts of this simulation. Now on the far right, you'll notice the outputs from this simulation. Now our goal, by changing a few of the inputs, is to minimize the fuel consumption, and then also to match a typical driving process. So we've come up with kind of an optimal battery state, and we want to evaluate or change our input variables to match this battery state of charge in a typical driving cycle. So our inputs in this optimization, we're going to vary the engine speed. We're also going to vary the state of charge. This is the battery level in which the internal combustion engine begins charging the batteries. We also decided to add a discrete input variable as the number of battery cells. This example is even more straightforward than the MATLAB example. You'll notice the input and the output nodes for MapleSim, and then the node in the center that calls MapleSim. We have grouped our input and output arrays so that we have a very straightforward process. Now, as we plan to begin the optimization, so we've taken this very complex model and we've created a very simple workflow inside of Optimus. As we begin the optimization, we know that we want to create a design of experiments with 200 experiments. Then we want to create a response surface, and finally run a multi-objective optimization on that response surface. So we begin with our Latin hypercube DOE that's automatically generated inside of Optimus, and you can see the response that's generated. Now these red curves that you see are actually Pareto fronts. So we begin to understand that there are some conflicting objectives here, that we do run into some limits in our performance and our fuel consumption. We've created a response surface, which is an interpolation along a mathematical interpolation based on the design of experiment runs that we conducted. On that response surface that you can see in the lower left image of the screen here, we can now change our variable values and arrive at a particular minimum or maximum on a multi-dimensional surface. This is showing 3 dimensions. We know from our problem setup, though, that we actually are working with a 5-dimensional problem. So we do have two competing objectives. We want to minimize the fuel consumption, and we want to minimize, we want to minimize the difference between the actual performance of the simulation and the optimal performance. So when we say minimize performance, we're simply looking to minimize the difference between what the simulation gives us and what we've already determined the optimal performance is, all while minimizing the fuel consumption. So the line that you see here is actually a Pareto front. The far left and at the top we have the experiment that gives us the ideal fuel consumption. The bottom right we have the experiment that matches the performance ideally. And then in the middle is a trade-off and is actually an optimal solution. For the multi-objective optimization, we determined that we were going to use another evolutionary algorithm that's specific to Optimus, known as the non-dominated sorting evolutionary algorithm, or NSEA+. We ran this optimization on that response surface, and this chart in the left side here gives us the results from that optimization. You'll notice that there are a number of points further out into the design space, but very quickly the optimization algorithm arrived at our Pareto front that you can see here on the left. The goal for each of these, again, is to have a lower value on the y-axis and a lower value on the x-axis as well. So let's take a look at the results. Our baseline values that you can see here, we have an efficiency of about 9.7 kilometers per liter, and a performance value, so this again is a difference from our design cycle or our optimal duty cycle, of 4,064. You can see the two optimal points on each end. 1 point increases the efficiency by 22%, but has very little effect on the performance. In fact, we go the wrong direction on the performance. As you can see, it's above the baseline. And the performance optimum, which improves our performance by 40%, but has very little effect on the efficiency. So we arrive at a trade-off, or an optimum value here in the middle that increases our efficiency by 16% and increases our performance by 27%. A very similar chart that we had before, for this, because this was a much more complex simulation, it took much longer to set up. In MapleSim, it would have taken about 240 minutes to set up. As you saw inside of Optimus, though, the setup was very quick and very straightforward. And so it only took about 20 minutes. The difference then in running these two optimizations was quite significant. We actually had a 37% reduction in the amount of time that the user had to interface with the model. And in addition to that 30% improvement, as we mentioned before, we increased the efficiency and increased the performance. Now, the last example that we'd like to show you is perhaps one of the more interesting examples. It's using Excel to actually drive or to get at, if you will, the functionality of Optimus. The typical customer that uses what I'm about to show you, I guess, is looking for a way to embed the functionality of Optimus in a scalable system that many engineers can use without having to go through training to learn how to use Optimus. That they can very quickly and in a very focused way get at the functionality of Optimus. Optimus has been designed with a number of Python hooks that all of the functionality inside of Optimus can be accessed. This includes the response surface models that we've shown, all of the different methods that we've shown, and a number of optimization and post-processing tools as well. So in this particular example, the user is using Excel to drive Optimus. Optimus then creates a workflow. It automatically creates a workflow that interacts with Ricardo WAVE, which is a 1D simulation tool. The first step that the user needed to go through in order to conduct this is to create a dashboard inside of Excel. They simply identified what methods that they wanted to make available to the user and then set only the parameters that they wanted to allow the user to vary. So for instance, they only wanted to allow the user to use one specific type of DOE and then to set the size of that DOE. In addition, the inputs, there are many hundreds of inputs to this Ricardo WAVE model, but they only wanted the engineers to have access to these 3 inputs. And so the engineer defines the boundaries for those inputs. The engineer can also specify a nominal method, so to do a single run, or a table method, which the example that we're showing does, where the user is able to input a number of different designs and then run all of these together. If the user would prefer, they have the option or the ability to run either a single objective optimization, this SOO, or a multi-objective optimization, this MOO, and then specify the objectives in these cells. In this situation, though, the user has selected the table method, has input 5 different experiments in the table, and then will select the Run button on the right, which calls a macro that launches Optimus in the background and submits each of these 5 jobs to Ricardo WAVE. After WAVE is complete, it reports the data back to Optimus. You can see being populated, there in the table on the right. And I will actually jump over to Excel so that you can see this dashboard inside of Excel. So let's take a look at the time savings with this particular setup. It still took about the same amount of time to create the model inside of the 1D analysis tool, about 35 minutes. But from there, the user did not have to enter the WAVE environment or the Optimus environment, and in addition, there was no amount of time that was required to set up the workflow inside of Optimus. And so they were able to save about 85% of the time. And it is important to remember that this is one user on one optimization problem. So this is a very scalable result. Now overall in MATLAB, we've shown how using Optimus can reduce an optimization time by about 50%. In MapleSim, we were able to parameterize a complex simulation and improve the performance by 25%. And when coupled with Excel, we were able to allow users that were not familiar with Optimus utilize the functionality, specific functionality inside of Optimus and save 85% of their time.